Hey guys, welcome back to my channel. Today, we're going to talk about the fabric of the universe itself, space-time. Two components of our reality woven together like a fabric. How do we traverse through space and time simultaneously? And what is this about time travel? Is it possible? Can we do it? Yes, we can. And we're going to find out just how today. So here we have a not-to-scale rendering of our very own solar system. And let's say in the far future, you and I decide to build a spacecraft capable of incredible speeds. And we want to visit a very interesting star system 20 light years away. So let's take a journey out there real quick. So we'll go out to this blue giant star, a distance of 20 light years from Earth. And we see an interesting planet here called a hot Jupiter. It's like Jupiter and it orbits very tightly to its parent star. Some of its atmosphere is even blown away by the interstellar wind. So, let's say my spacecraft can travel up to whatever speed I want, 99.9999% the speed of light, and we decide that I'm going to take a journey to this star system using the ship's engines to travel at a measly 98% the speed of light. So, at 20 light years away, how long will you say the trip took, round trip, for me? So we have a distance of 20 light years, so that's where we'll start. Our ship can't quite go light speed, so what we can do is a little bit of dimensional analysis to show that in 1 year time, our ship, programmed at 98% the speed of light, can't travel 1 light year, it can travel 0.98 light year. The light years, of course, will cancel for us. Now, it's just a simple math problem. So we take in our calculator 20 light years distance divided by our proportional speed, 0.98, and we get a round trip time, or a trip time, of 20.4 years. Now, because we're going there and back, we need to multiply this by 2. And you will say the trip took me approximately 40.8 years. So when I return to the Earth to say my mission was a success, you'll expect me to be 40 years older. But to your shock, not only do I say, that trip didn't take me 40 years, you'll find that when I return, you will be older than I am. So how is this possible? Well, we're going to take a look at that in our next little segment.
Oh no, Pluto, stay!
Row! Row!
Einstein was the first person to realize that the speed of light in our universe had to be preserved. That meant as a traveler approached the speed of light, time for them would slow down. We call this time dilation. And we don't notice it in our everyday goings about because it doesn't become noticeable until we reach very near light speeds. Let's take a look at a graph and see what the relationship looks like. If we put on this axis the amount of dilated time, so how much is time stretched or compressed by? We'll call this t prime. And on this axis, we'll put our speed, we'll call v. And at the end of this is the speed of light, c. Under normal conditions, if your speeds are nowhere near the speed of light, the amount of time dilation isn't very much. But as you begin to approach c, time begins to dilate more and more until the graph becomes almost linear. So at the speed of light, time for the person traveling at those velocities would be very nearly stopped. So what does that mean for our little ship experiment? Let's take a look at the equation that governs this entire thing. So here we have Einstein's time dilation equation, where t prime, the amount of dilated time, this is the time that the person in the ship would experience, is equal to t, what we call standard time or stationary time. This would be the amount of time you would experience on the Earth if we're doing this experiment together, times the square root of the quantity 1 minus v squared, that's your speed in the ship, over c squared. Now, these velocities, like the speed of light we know is 3 times 10 to the power 8 meters per second. Our speeds are going to be extremely high if we're traveling at fractions of the speed of light. So the numbers could get complicated really quickly, except we can use a trick. As long as we're doing this in fractions of the speed of light, we can use percentages. So 20%, 30, 40, 50% the speed of light, and we all know that those percentages can be expressed as decimals, 0.2, 0.4, 0.6, so on. So let's do our problem now and see how much time did I really experience in the ship. So we're going to plug in the numbers we've already calculated. We know that you on the Earth observed me using normal Newtonian mechanics to take 40.8 years. So that would be our stationary time, 40.8 years. We're going to multiply that by this quantity, sometimes called the gamma factor, 1 minus v squared, which in our case, v squared was the velocity 0.98. So we're going to replace that with 0.98 squared. And if we're expressing this as a fraction, well, the speed of light is 100% the speed of light, so 1 squared. So we have 0.98 squared over 1 squared, which is 1. That quantity, 1 minus that, the square root of that. It's important that you do these in your calculator step by step, otherwise you're likely to get a mistake. Don't try to plug it all in at once. Do the gamma quantity first, 0.98 squared, then take that 1 minus that, the square root, multiply that then at the end by 40.8. So what does this all come out to? Well, I've done the calculation ahead of time for you, and what we find is that t prime, the amount of time I experience on the ship, ends up only being a little bit over 7.8 years. So you will have experienced over 40 years of time. So if you're 18 now, you'll be 58 years old when I return. But I'll have only experienced a little over 7 years of time. So when I return, I'll only be 38 years old. So you will be older than me when I return. And that's the power of time dilation. So give those worksheet problems a try that I posted earlier on Schoology. If you have any questions, let me know through Remind, and I'll be happy to address them. See you here next time, guys.